also asking us what would be the gain value required so that all our closed loop poles are on the right half plane. So let's start off with again just drawing our imaginary plane. So that's what we have. And again, here since they're not specifying that they want you to draw this by hand, probably we don't need to be too precise, or you can use a MATLAB plot as well. But just to quickly sketch out a root locus, since everything is factored out already, let's start off with let's start off with the poles. So we have one pole at 3, another pole at -5, and then we have zeros at -2, and then -2j, and then also positive 2j. If you were to plot this, you will end up with something like that. We have a breakout point somewhere over here. And it looks something like that. So again, I think I'll attach a MATLAB plot of the root locus as well. But this is what it would kind of look. So now what they're asking us to do is find out the gain value for which the closed loop poles will be on the right half plane. So that's in a way again talking about stability in a sense. So we have to make sure that they are if they are on the right half plane, it's not stable. If it's on the left half plane, it is stable. So if you go back and use the characteristic equation for this entire system and use the root array, you will end up with the right answer. But there is a bit of a shortcut that we can use that works out for this problem particularly. So I'll show that shorter method right now. But if you do the root array, that will also give you the same and correct answer. But it is a little bit lengthy, and you will end up with slightly complicated expressions in your first column. So this works out a little more easily. So that option is always there if you do decide to take it, and it will give you the same answer. But if you want to use the shortcut, this is based off something that Dr. Guvenk mentioned in lecture 26, slide 27. And what he said was that the gain at any point on the root locus can be found out if with this expression. Right? So essentially what he's saying is that let's say if we had any point on our root locus, any arbitrary point. So let's say if this was the point that I'm talking about. I can find the gain at this point on the root locus by calculating these different distances that this point makes with the poles and the zeros of the system. And then we want to take the product of the lengths of the poles in the numerator and the product of the lengths of the zeros in the denominator. So for this particular problem, since they are asking us, we need to find the gain for which the system is going to be in the right half plane, we know that our criteria is kind of making sure that the root locus points, or rather all our poles, are in the left half plane, or that criteria also works. It would be just the inverse. So essentially we just have this one root locus segment between -2 and 3, this one over here, which can cause the poles to be in the right half plane, right? So what we want to do, we want to make sure that if you were looking at this point here, which is at the origin, what would be the gain at that point? If the gain is more than that, it would mean that everything is in the left half plane and that's stable. If it's lesser than this gain value over here, then you would have one pole over here, and that would not satisfy our criteria. So if you're looking at this point over here, we are looking at these lengths, right? And since it's the origin, all of the lengths work out very nicely, right? And so in the numerator we have nothing but 5 times 3. Since our one pole is at a distance of 3, another pole is at a distance of 5. Key word to note here that it's length, not displacement, so the sign does not matter. So even if it's on the negative side, it's -5, but the length is just 5. And in the denominator we have the length 2 coming in from the -2, 0, and then another length of 2 from the vertical pole, from the vertical 0 at the top, and then one more 2 from the vertical 0 at the bottom. So the gain at the origin is 15/8. And that is your critical gain kind of cutoff value, essentially. So if we want everything to be in the left half plane, we want the gain to be greater than 15/8. If we want it to be in the right half plane, we want it less than 15/8. Does that make sense? Any questions? Yeah.
So is that the range then? The right half plane is less than 15
Correct.
eighths, that's what your gain is.
Mm-hmm.
So like I did the Ralph array
Mm-hmm.
method, and I found 15 eighths, so it has to be less than, but then I also found, like I wasn't sure how to do it exactly, because like obviously if you have your coefficients in that first column and you know how many positive poles you've got based on how many sign changes there are, it's like I pretty much just rigged it so that there was only one sign change.
Right.
And so I found the 15 eighths, but then I also found that you couldn't go under 0, so that was my range. But like I just wasn't sure like how.
Right. So I think I did it with the Ruth array as well. So I think in that I ended up with like 2 criteria that it needed to satisfy. I think one was that k has to be greater than -half or something like that,
Okay.
and then one was that k has to be greater than 15/8 or something like that.
Yeah.
So the 15/8 kind of trumps the other criteria, because that one also has to be satisfied. So that one condition of k greater than being 15/8 kind of is valid for your entire first column of your Ruth array.
Okay.
Yeah.
Okay.
All right. Any other questions?